Namaskar and welcome to this series of lectures titled Heat Transfer. The subject is meant for undergraduate students in mechanical engineering, and the contents of the subject will also be useful to other disciplines of engineering such as chemical engineering, aerospace engineering, aeronautical engineering, metallurgy engineering, etc. So, here in this course we will cover the fundamentals of heat transfer, different modes of heat transfer, and then we will try to solve problems on heat transfer. So, where this knowledge will be used for solving some real life engineering problems. In our day to day life, we are very much acquainted with the process of heat transfer without knowing the underlying principles. For example, starting from our kitchen, where on a day to day basis we deal with heating for the purpose of cooking. So, myself Dr. Manoj Moharana, presently serving as a faculty at the Department of Mechanical Engineering, NIT Rourkela. So, my office is situated at the first floor of this cryogenics laboratory, and you are encouraged to contact me through phone or this email as given here for any difficulty related to this course. The regular updates related to this course will be available on Facebook at the following link, and the video lectures for this course will also be available on this YouTube platform at this following YouTube channel. The details of the course content of this series of lectures on heat transfer will be available on this website, where you will get the detailed content of each and every lecture to be covered throughout this semester. The title of this course is Heat Transfer, the subject code is ME451. So, this is a 4 credit course having 3 lectures and 1 tutorial, that means you will have 4 number of classes every week. So, these are the class timings. Considering that it is level 1 course for undergraduate students, ideally no prerequisite is required to study this subject, but it will be good if you recall the knowledge of thermodynamics that you have already covered during your first year or second year of your undergraduate engineering program. Considering the nature of this course, if you know the concept of differential equation, then it will be easy for better understanding. Considering that undergraduate students will be studying this course heat transfer, and before this one they have already studied courses titled engineering mathematics, there they have already covered. So, this concept they should try to recall if they do not remember things now. Then here throughout this course we will be going to draw some 2D plots as well as contour diagrams for temperature information through the domain of different engineering problems. So, if you know use of any of commercial plotting softwares or any free software, then it will be very much useful to you. So, for example, Microsoft Excel, though it can do many things, here in this course we will be using for making 2D plots here. Then this origin and tech plots, they can help to go for making your contour plots for temperature information of over a 2D or 3D domain. The objective of this course is to introduce the fundamentals of this heat transfer, to develop methodologies for solving wide variety of real life engineering problems involving the concept of heat transfer. So, it is expected that after completing 1 semester of study with some optimum effort towards understanding this subject, a student should be able to understand the fundamental principles and mathematical basis underlying the balance equations of heat transfer. Then the student should be able to analyze problems involving steady and unsteady heat conduction, and problems involving convection, and problems involving radiation in different geometries. Then the problem should also be able to solve some real life engineering problems such as heat transfer enhancement through extended surfaces like fins, then unsteady problems involving lumped heat capacity systems, problems involving heat exchangers, boiling and condensation, and calculating view factors for radiation heat transfer problems in different geometries. This outlines the overall the course content for this lecture of series on heat transfer. So, first we will go for basic introduction to the heat transfer, then we will go for a detailed study of each and every heat transfer modes like your conduction heat transfer, then convection heat transfer, then there is a third mode that is also a radiation heat transfer. Before you go for this radiation heat transfer, we will go for applications of this convective heat transfer, that is your boiling and condensation, where phase change phenomena takes place. Then we will use heat exchangers and we will study in detail about them, and then finally, we will conclude the semester with a study of this radiation mode of heat transfer. So, overall in addition to the basic or fundamental theory underlying all these theory things, we will try to solve many engineering problems involving this concept, so that we will be able to understand the background principles behind them. Regarding reading materials, this is a textbook which is a very classic textbook used throughout the world, recommended for the students. Though there are infinite number of internet sources are available for the students, like your YouTube videos, websites, etc. It is always recommended to have at least one hard copy textbook on your desktop for ready reference, so that you can refer it back to the textbook anytime. So, this textbook titled Fundamentals of Heat and Mass Transfer by Incropera and DeWitt will be recommended a very good book. So, here in this new edition of this textbook, you will find out two more authors like Bergman and Levine. Then this is another textbook on heat transfer by Professor P. S. Ghosh from IIT Kanpur. So, this book is from Oxford University Press. There is another textbook recommended, that is Heat and Mass Transfer Fundamentals and Applications from McGraw-Hill Education by Eunice Sengel. This is also economy edition available in the market. Then there is another good book titled Introduction to Heat Transfer by Professor S. K. Som from IIT Kharagpur. So, this book comes from PHI Publications. Then there is a heat transfer by J. P. Holman, and in recent times there is addition of a new author to this text, and now this book is available in the Indian in the economic editions from this McGraw-Hill Education. Then there is a textbook titled Heat Transfer by A. F. Mills and B. Ganesan, published by your Pearson Education. So, in addition to these 6 textbooks recommended here, there are many textbooks available in the market. Students are encouraged to refer any of the textbooks which they feel comfortable, and you can find out details of any heat transfer textbook by taking the help of Google Books, where you can use the keyword heat transfer. This will suggest you many textbooks that are available in the market. Now, considering the title of this subject heat transfer, the first question comes to our mind is, what is this heat transfer? So, already by the time you have already covered a subject, your engineering thermodynamics, during your first year or second year of undergraduate program, where in thermodynamics we have very much dealt with the word heat. There we studied that whenever you have a system, let us say at a temperature T1 and there is another system at a temperature T2 and this T1 is not equal to T2, then there will be transfer of heat from the high temperature point to the low temperature point. So, this heat can be defined as the form of energy that can be transferred from one system to the another system because of difference in the temperature between these two systems. So, here let us say we consider T1 is the temperature of this system and T2 is the temperature of this system, and here we assume that T1 is greater than T2, then in this case there will be flow of energy from this system to this system. And if the reverse is true, that means if temperature T2 is greater than T1, then the direction of arrow will change here in this case. This thermodynamics you have studied, basically it deals with the end states only, that means it deals with the end equilibrium states only, and here it does not talk about the time rate of occurrence of this interaction. That means, in between these two equilibrium states what happens, we basically do not study in the subject thermodynamics. Whereas, in this present subject titled heat transfer, here basically we will study about what is happening in between these two equilibrium states. So, here the heat transfer is nothing but you can say it is the science that deals with finding the rates of such energy transfer from one system to another system because of difference in temperature between them. So, we can define this heat transfer as the thermal energy that is in transit due to the temperature difference between these two systems. And always considering that this heat transfer deals with what is happening in between these two equilibrium states, always this heat transfer will lag the thermal equilibrium process. There are different modes of heat transfer available. So, we can have three basic modes of heat transfer known as conduction, convection and radiation mode of heat transfer. There are some group of people who argue that there are only two modes of heat transfer, conduction and radiation only, and this convection is nothing but another form of conduction mode of heat transfer. But here we will consider that there are three modes of heat transfer, and accordingly we will go for the study in detail about them. So, first we will study briefly about what is conduction and what is convection and what is radiation mode of heat transfer. Then again we will revisit to each and every mode of heat transfer in detail. So, first we will go for this conduction heat transfer. So, to understand this process of heat transfer, we will start with a very simple experiment, for which we need to consider, let us say, a metallic rod you take. Let us say we will consider a copper rod or a silver rod or a aluminum rod. Then you consider some small candles, you take these candles and you try to put them above this rod vertically at some equal distance intervals as shown here in this case. Then you take another candle at the other extreme end and then you enlighten the flame of this candle here. So, now this energy produced by this candle will start hitting the one end of this metallic rod. So, now here we will go for the microscopic view of this metallic rod. So, here I have represented one row of molecules present in this metallic rod. So, the molecule that is exactly above this candle will first gain some energy and its temperature will go up. So, then it will give some energy to its neighbor because of its interaction with its neighbor molecule. So, in the process the second molecule, that is the molecule to its right side of this molecule, will also gain some energy and its temperature will increase. Then this will again give some energy to its next neighbor. So, like this there will be transfer of energy from the left to right. So, one molecule to another molecule by increasing in their temperatures. So, when the molecule below this candle gains energy, then the temperature here will increase, that is the temperature on the outer surface of this rod below this candle will increase, and when this temperature exceeds the melting point of this candle, wax candle, then this candle will fall down. Then again this the heat transfer process will continue here in this direction, then the second candle will fall, then third candle will fall, like this subsequently all the candles will come down. So, here you will see this candle falls down because of transfer of energy from this one end of this metallic rod towards the other end, which cause melting of the base of this candle, and because of the gravity the candle comes down. So, here we can say the conduction is nothing but a transfer of energy from a more energetic particle, that means this, let us say you say this is the energetic particle, to its adjacent less energetic particle because of interaction between these two particles. So, the particle having higher energy will give the energy and the particle having the lower energy will receive the energy. So, in the process there will be transfer of energy from the more energetic particles to the adjacent less energetic particles. Now, we will go for another simple experiment. Let us say you take a hot cup of coffee or tea, then you put one spoon there, then you will see after fraction of seconds the other end of the spoon will get heated. This is also because of the same phenomena. That means, the portion of the spoon that is inside this hot coffee or tea gets heated by taking energy from this hot liquid, and there will be heat transfer by means of conduction as explained here and towards the other end of the spoon, and you will feel the other end of the spoon is also heated. So, here also this is the first molecule which gains energy from this hot coffee or tea, then its temperature increases, then it gives some energy to its neighbor. So, this second neighbor is towards the other end of this spoon here. So, in the process there is a heat transfer by means of conduction along the length of this spoon. So, next let us say we consider a system where we will take 2 points, let these 2 points we will name as A and B. So, there will be transfer of heat from point A to point B or from point B to point A depending on what is the temperature at point A and temperature at point B. So, if the temperature at point A is greater than the temperature at point B, then the direction of energy transfer will be along this arrow, and if the temperature at point B is greater than the temperature at point A, then the direction of flow of energy will be along this direction. And here in the two examples we consider, we discussed about flow of energy through a solid medium. So, now question arises, does conduction takes place in solid only? The answer is no. Conduction can also happen in liquid also, in gas also. So, we can say that energy transfer by conduction can occur in solid, also in fluid, which includes liquid and gas. In case of solid, this energy transfer by conduction takes place because of combination of lattice vibration and the free electrons. So, in first case the heat transfer or the energy transfer in the solid medium will be because of this lattice vibration, the concept as I have explained here. Secondly, in case of metallic solids, there will be presence of free electrons which are moving inside this solid within its limitations, and these free electrons, if they are having higher energy, they will transfer energy to other molecules when the other molecules in its neighbor are having less energy. Similarly, in case of fluids which include liquid and gases, there will be transfer of energy from one molecule to another molecule whenever there is a collision. We know that molecules move within some limitations inside the domain, and the movement is smallest in case of solid and it is the largest in case of gases, and this movement is intermediate value in case of liquids. So, the molecules collide with each other more frequently in gases compared to solids, and it will be intermediate value in case of liquid. That is why whenever a high energetic particle collides with a low energetic particle, then it will transfer some amount of energy. Then the question arises, does every time there will be a heat transfer by means of conduction in fluid? The answer is no. The condition for heat transfer to takes place by means of conduction is that there should not be any motion of the fluid particles, that means the fluid particles should be at rest. So, here we will see that conduction is the only mode of heat transfer that occur in case of non-transparent solids, because if it is a transparent solid, then later on we will see that a radiation mode of heat transfer can also takes place. Then here we will see that in conduction what we are going to do actually. Here we will see that in the study of conduction, our objective will be to determine the temperature distribution inside the body and calculate the flow of energy inside this solid, considering that we are studying conduction in the solid mediums. So, here whenever we go for solving any problem, we will try to find out what is the temperature at each and every point inside the domain of the problem. Then we will be interested to find out how much is the flow of energy takes place from one point to the another point. it is to note that heat transfer cannot be measured directly, but we can derive the value of heat transfer or the flow of energy by measuring some other parameters like measuring the temperature at different points. The values we obtained by measuring the temperature at different points will help us to calculate the amount of flow of energy in a particular problem. So, regarding this temperature distribution, it is nothing but it is a variation of temperature at different points. We know that there are 3 directions in a coordinate system. Let us say we will first take about Cartesian coordinate system, where we have 3 directions x, y and z direction. In addition to these 3 x, y and z direction, there is an imaginary direction, we can say it a time direction. So, the temperature can vary in a domain along the x direction, along the y direction, along the z direction independently or simultaneously, and along with these 3, temperature can also vary inside the domain with respect to time. So, we can say you will having 4 directions here in this case. So, when you consider this temperature distribution, we will consider space along with time t. So, in generalized manner we can represent this variation of temperature as T inside bracket x comma t. So, this indicates that temperature T varies with space x, also it varies with time small t. So, if we consider it to be one dimensional problem, that means if we neglect the variation of temperature along 2 more direction, that is, let us say we consider that temperature T is varying along the x direction only and it is not varying along the y and the z direction, then we can say that it is a one dimensional problem, and when temperature is not varying with time t, then we say it is a 1D steady state problem. So, in that case temperature T will be purely function of x only. If we consider that temperature is also varying along the time t in addition to variation along the space x, then we will say it is a one dimensional unsteady problem. In that case we can represent this T bracket x comma t. Then when you consider temperature is varying along 2 directions and it is constant along the third direction, then we say it is a 2 dimensional problem, and if you consider temperature is constant with respect to time, then we call it a 2D steady state, then in that case we can represent as T x comma y. Similarly, for a 2D unsteady conduction problem you can write down it is a T x comma y comma t. Similarly, for a 3 dimensional problem you can write down 3D steady state, you can represent like this T x comma y comma z, and for a 3D unsteady conduction problem you can write down as T x comma y comma z and small t, that is representing your time. So, let us say you consider here this is the 3 dimensional geometry. Actually, you will see though we are studying about 1 dimensional and 2 dimensional things, in reality nothing exists as 1D or 2D, all things in real life are 3 dimensional depending on the situation, and to simplify the problem we assume it to be a 2 dimensional or 1 dimensional depending on the cases, and in some cases it will be wrong to assume it to be a 2D or 1D problem. We have to consider it to be a 3D problem only, and we have to solve the actual problem. So, next we will go for something called your Fourier's law of heat conduction. So, this law will give us idea on how to calculate the amount of energy transfer or heat transfer by means of conduction. So, this Fourier's law of heat conduction is based on the continuum assumption, and its origin comes from experimental observation by a scientist known as Biot, and later on based on the experimental observation noted by the scientist Biot, another scientist called Fourier proposed this law for heat conduction, and he wrote a textbook on this subject titled The Analytical Theory of Heat in the year 1822, originally written in the French language, whose French title is as given here. So, let us say first we consider a slab, and here we will consider it to be one dimensional heat conduction problem by considering the temperature T varying along the thickness of the slab only. Temperature T is not varying along the other 2 dimensions, along this direction and this direction. And here let us say temperature on the left face is a constant value T1, temperature on the right face is a constant value T2, and this A is the area of these two faces where it is perpendicular to the direction of transfer of the heat or transfer of energy. So, if we consider that T1 is greater than T2, then in that case the direction of heat transfer will be from the left face toward the right face, as shown here in this arrow here. It is found that the heat flow in this situation from this left face to this right face is directly proportional to the area which is normal to the direction of flow of the energy, and this heat flow is also directly proportional to the difference in temperature between these two surfaces, that is this heat transfer Q directly proportional to T1 minus T2. Then this heat flow is inversely proportional to the thickness of this slab. So, here you can say when this area A increases, heat flow increases, when the difference in these two temperature increases, heat flow increases, but when this thickness you increase, the heat flow decreases. Or you can represent this one, Q will be equals to K into A into T1 minus T2 by L, where this K is nothing but your constant of proportionality. So, here we can rewrite this expression by introducing a negative sign here. So, that this T1 minus T2 we can write down to be equals to T2 minus T1. So, this heat flow Q in this system can be represented as minus K into A into T2 minus T1 by L. So, if we consider the differential concept, then here let us say you consider this is the variation of temperature in the domain, and we consider a small elemental strip here. So, here you will have some temperature at this point, another some temperature at this point, and the differential element width will be dx, and for which the temperature difference will be dt here. Then you can rewrite this expression as Q equals to minus K into A into this term can be written as dt by dx, where dt by dx is nothing but the temperature gradient in the solid medium. And here this constant of proportionality K, that is known as the thermal conductivity of the solid medium, and this thermal conductivity is nothing but it indicates the ability of the material to conduct the heat. That means, the higher the thermal conductivity of a medium, the easier it is for heat flow. The lower the thermal conductivity of the medium, the difficult it is for the heat to flow through the solid medium. And this thermal conductivity will be a thermophysical property of this solid. That means, from one material to another material, the value of this thermal conductivity will vary. And this dt by dx as told, which is nothing but this temperature gradient, which you can find out as the slope of this temperature curve on a Tx diagram, if you draw for the variation of temperature from the left face to the right face inside this slab. And this heat conduction in the direction heat will be conducted, that means as shown here in this arrow, it will be in the direction of the decreasing temperature. That means, heat flows from the high temperature to the low temperature, and this temperature gradient in such case will be negative when the temperature decreases along the positive x direction, and when temperature is decreasing along the negative x direction, then in that case the temperature gradient will be positive. So, that we will see again here, and here in the expression for the heat flow, the negative sign in this expression, it actually ensures that heat transfer will be along the positive x direction, will be a positive quantity, because along the positive x direction this temperature gradient dt by dx is negative. So, negative of negative will make it positive. So, it will ensure that heat flow will be a positive quantity along the positive x direction. So, now you recall this expression Q equals to minus K into A into dt by dx. So, this is nothing but the expression for heat conduction to find out. Then you can rewrite it like this by taking this area to the other side. So, this becomes Q by A on the left hand side equals to minus K into dt by dx. So, heat flux per unit area, that is Q by A, is nothing but your heat flux per unit area. So, that you can represent as Q double prime on the left hand side. So, that becomes minus K into dt by dx, its unit will be watt per meter square. So, now let us say we will consider two types of variation of temperature along the space x. In one case temperature T is decreasing along the positive x direction, and the second case temperature T is increasing along the positive x direction. So, here we can consider any particular location x, let us say here you consider this location. So, we will go for drawing the calculating the slope of this curve at this location. So, here at this point we will go for a tangent to this curve, and here you can find out what is the slope of this curve here. So, here you will find out that dt by dx will be less than equals to 0, that means, in this case it will be a negative value. Because of this you will obtain the heat flux or the heat flow, it will be along the positive x direction will be a positive quantity. So, this will be the direction of heat flow, and the heat flux conduction heat flux will be a positive quantity. So, you will have a plus q double prime. Similarly, in the second case where the temperature T is increasing along the positive x direction, again let us say we go for making calculating the slope at the same point. So, here at this point you go for the tangent and you calculate the slope, and in this case this dt by dx will be a positive quantity, and if you use this expression here dt by dx is positive. So, from here you will get this conduction heat flux, that is q double prime will be a negative quantity. So, that is why the direction of heat flow will be towards the negative x direction. So, here you will have a minus sign here, or this will indicate the direction of the flow of the heat. So, let us say you consider the one dimensional heat flow in this solid wall. So, having a thickness let us say L here as shown here in this diagram, and let us say we will consider one simple example. Left face is at let us say constant temperature of 85 degree centigrade, and this right face is at a constant temperature of 35 degree centigrade. So, there is a difference in temperature between the left and the right face. Considering that left face is at higher temperature, right face is at the lower temperature, there will be flow of heat by means of conduction from the left face to the right face. And let us say we consider this L to be equals to 2 meter here in this case, and the thermal conductivity of this medium let us say equals to 100 watt per meter Kelvin. So, in this case first we will go for calculating how much heat flow takes place from the left face to the right face. So, that we can calculate by using this basic expression that we obtain from the Fourier's law of heat conduction, that is q equals to minus k into A into T2 minus T1 by L. So, here T2 indicates temperature on the right face, T1 indicates temperature on the left face, or in terms of heat flux, that is heat flow per unit area, this will be minus k into T2 minus T1 by L here. So, now using these appropriate values, by using in this expression we can calculate the value of heat flux per heat flow per unit area, that is conduction heat flux, which comes out to be 2500 watt per meter square. Similarly, let us say we will consider another situation for the same geometry. The left face let us say is at a temperature of 15 degree only, whereas the right face is at the same temperature as previous case, that is 35 degree centigrade. That means, here in this case left face is at a lower temperature, whereas the right face is at a higher temperature, that is this is a reverse case of the earlier one. So, in this case we expect that the heat transfer will be from the right face to the left face. That means, here we will go for calculating similarly as we did for this case. So, here when you use this expression again using the appropriate values, we will obtain the heat flux or heat transfer per unit area comes out to be minus 1000 watt per meter square. So, the total heat flow between these two surfaces is equals to 1000 watt per meter square, but we are having a negative sign. The negative sign indicates that the heat flow is in the direction opposite to the positive x direction. That means, heat will flow along the negative x direction, that means, the heat flow will from the right face to the left face. So, here this will be the direction of heat flow, and here this will be the direction of heat flow, because in this case you get a positive quantity and in this case you get a negative quantity. Next we will go for solving a problem based on this concept, a very simple problem which states that 1 kilowatt of heat conducted through an insulating material as shown here, where its thickness is 40 centimeter. The left face is at a temperature of 100 degree centigrade, and you have been asked to find out what is the temperature on the right face. The area normal to the direction of heat conduction A is given to be 20 meter square, and the left surface is temperature is given, and you have to find out the temperature on the right face. Then the thermal conductivity of this material is also given to us, which is 0.5 watt per meter Kelvin. Then the second part of this question says that if the heat conducted through the insulating material increases 5 times the previous value. So, initially it is given 1 kilowatt, and second time let us say instead of 1 kilowatt we want that the heat transfer should be 5 kilowatt. Then what should be the new temperature on the right surface? Then you have been asked to state your observation about this. That means, go for a comparison between the first situation and the second situation. So, here first you will note down what are the information given to us. So, the first, the Q value is given, that is 1 kilowatt, that is 1000 watt. Surface area A is given to be 20 meter square, and then this thickness of the slab or dx or L is given to be 40 centimeter, which we can write down to be 0.4 meter. Then thermal conductivity of this metal is given to be 0.5 watt per meter Kelvin. So, here first we will write down the expression for heat flow Q from the Fourier's law of heat conduction, that is minus k into A into dt by dx. Here Q is known to us, area is given, k is also known to us, dx is also known, and in dt we know one value of temperature on the left face, and we can find out the only one unknown in this expression, that is temperature on the right face. So, now we will use this expression here. So, dt I write down as temperature on the right face minus temperature on the left face. So, here Tr is unknown, TL that is known, that is 100 degree centigrade. So, you can use these values here, and once you put the known values and you go for the calculation, you obtain the temperature on the right face comes out to be 60 degree centigrade. That means, if you maintain temperature on the right face to be 60 degree centigrade under the situation given to you, there will be a net 1 kilowatt or 1000 watt of heat flow from the left face to the right face, because left face is a higher temperature and right face is at a lower temperature of 60 degree centigrade. Here it is to note that for the temperature on the left face I have used the direct value of 100 degree centigrade, considering that both these two temperatures are in degree centigrade and their difference will be also in degree centigrade. But normally one should make a practice to solve problems first converting this degree centigrade into Kelvin for avoiding mistakes while solving the problems. But you can consider the unit of degree centigrade whenever there is a difference in temperature. Then now we will go for solving the second part of this problem, where it has been told that heat conduction through this insulating material increases 5 times. That means, now the heat transfer Q will be 5 kilowatt, that means 5000 watt. So, we will again use the same expression as we have used here, this one here. So, in this expression left hand side we will have a 5000 watt, that is equals to minus k into A into Tr minus TL by dx. So, here in this expression on right hand side you know everything except the temperature on the right surface. So, on calculating this one you will obtain temperature on the right hand surface comes out to be minus 100 degree centigrade. That means, you have to maintain a negative temperature on the outer surface, right hand side surface, then only you can increase the heat transfer 5 times compared to the previous situation where temperature on the right surface was maintained at 60 degree centigrade. So, you can find out how much is the difference in temperature you are maintaining here. In the first case, left hand side is 100, right hand side is 60. So, the difference in temperature is 100 minus 60 comes out to be 40 watt. Whereas, in the second situation, left hand side is at 100 degree centigrade and right hand side is minus 100 degree centigrade. So, 100 minus of minus 100, so it makes your 200 degree centigrade. That means, earlier it was 40, now it is 200. So, it is your 5 times. So, because of this 5 times increase in the difference in the temperature, you are able to increase the heat transfer between the surfaces by 5 times from 1000 watt to 5000 watt or from 1 kilowatt to 5 kilowatt. So, next before you go further detail into conduction, we will first understand the concept of convection, then the concept of radiation, and after that again we will return back to this point where we have stopped here regarding the mode of heat transfer is conduction. So, next we will go for convective heat transfer. So, here to understand the concept of heat transfer by means of convection, let us take a container and you take some water and you add heat from the bottom. So, here I am considering the zone nearer the bottom surface of this container here. So, in this case you see this represents the solid portion and this represents the water in the container, and here we are going to add heat at the bottom. So, that means the solid will gain heat and there will be conduction in the vertically upward direction here in the solid. Then there will be transfer of heat from the solid to the adjacent fluid. So, now here we will understand how the transfer of heat takes place from the solid to the adjacent fluid. Earlier in conduction we studied how heat transfer takes place inside this solid domain. Now, here let us say you consider a molecule of the liquid which is in direct contact with the solid. So, this is the molecule which is in direct contact with the solid. Now, solid is at higher temperature. So, the molecule in the solid which is neighbor to this liquid molecule will give some energy to this one, as a result its temperature will increase. And when temperature of this water increases, its density decreases, that means it becomes lighter, and at the top you are having a heavier water molecules. So, this molecule will try to move upward because of the buoyancy force it will act on this one. So, then a vacancy is created, then another molecule will occupy this position and the process will repeat. So, this molecule will also again gain heat from the solid, then when its density again decreases it will again move. So, this will become a continuous process, but here it is to remember that this is a still in the liquid is in the single phase only there is a increase in the temperature. So, this mode of heat transfer to the fluid because of movement of these molecules, we call it to be the convection. So, we can define the convective heat transfer is nothing but it is the mode of energy transfer between the solid surface and the adjacent fluid which are in contact with the solid. So, this fluid it can be a liquid or it can be a gas also, and this liquid and gas they will be in the motion, and because of this motion they carry out some heat from the surface. So, this will be a continuous process, and this convective heat transfer consists of two mechanisms. One is that there will be transfer of energy because of random movement of these molecules, which we can say because of the diffusion, which is nothing but the conduction mode of heat transfer. Then there will be movement of these molecules of the fluid at large. That means the distance travelled by these molecules will be very bigger. So, in that case also they will carry some amount of heat far away from the solid surface. So, the heat transfer from this solid wall to the ambient fluid will take place by means of direct conduction near this boundary, as well as because of convection because of the movement of the fluid away from the surface. So, this total heat transfer that takes place from this hot surface we can consider to be some of the two modes of heat transfer. First one is energy transport by random motion of these molecules, second one is energy transport by the bulk motion of the fluids, that is movement of the fluids far away from this hot surface. And here we will use two terms, one term is called convection and second term is called advection. The term convection we will be using to refer to cumulative transport of energy, that is transport of energy because of random motion of the molecules plus transport of energy because of the bulk motion of the fluid. Whereas, we will use a new term called your advection, which will refer to the transport because of the bulk motion of the fluid only. That means, the fluid which is moving from the surface towards from the surface, it is moving away from the surface, which carries some amount of energy, that we call as the advection. So, here in this case we call this to be your convection, whereas this we call to be is equal to advection. That means, convection is nothing but sum of heat transfer by conduction plus heat transfer by means of advection. So, here we can classify the convective heat transfer into two types based on the nature of the fluid flow near the wall of a solid surface. So, here we can have two types. So, first one is called your forced convection and the second one is called your free or the natural convection. Already we have understood that there will be movement of the fluid away from this solid wall because of buoyancy force acting on the molecules due to decrease in the density because of the increase in the temperature. This is called the free or natural convection, because this process happens automatically without any external power input, whereas forced convection is nothing but the heat transfer to the fluid because of movement of the flow caused by some external power input. So, to make this forced convection, we can use some external power input for movement of the fluid. For example, let us say here in the same container where now this water is still, we will consider one small fan or stirrer, and this shaft of the stirrer we can connect to a small motor, and when you give power to the motor, the shaft of this stirrer will rotate. As a result, there will be movement of this liquid inside this container, which will cause the heat transfer by means of forced convection. So, the energy transfer that will happen in this situation as described here in this problem will be by means of two ways. One is called your sensible energy transfer and second one is called your latent energy transfer. The sensible energy transfer indicates the transfer of energy from the solid to the ambient fluid because of single phase heat addition, or it may be a reverse process, single phase heat subtraction if we are cooling the liquid. Then the second one, latent energy transfer, indicates there is a change in phase of this liquid which is near this hot solid. So, the change in phase from it can happen from liquid to vapor or it can be from the vapor to liquid. So, the phase change from liquid to vapor will takes place when we go for addition of heat to the fluid, and when you go for extraction of heat from the fluid, then there will be a change in phase from the vapor state to the liquid state. So, to indicate these two processes, there are two separate words. So, here you will see how in this present situation there will be change in phase from liquid to vapor. You will see here initially let us say the fluid is having at the ambient temperature and this wall is maintained at let us say certain constant temperature. So, because of conduction and convection, there will be gradual increase in the temperature of the water. When the temperature of the water reaches to the saturation temperature of the water corresponding to the pressure, where in the present case it is the atmospheric pressure, that means here for water it needs to reach 100 degree centigrade, then in that case you will see liquid will start converting into vapor. So, near the surface small bubble will be formed, and with gradual addition of heat this size of this bubble will increase, and once the bubble achieves to a certain size, the bubble will it will start moving vertically upward. So, this will happen because of the buoyancy force it will act on this bubble, and when this bubble will move upward, it will also create a disturbance to the surrounding fluid, then there will be movement of the water in this container. So, here this change in phase from this liquid to vapor, that is called your boiling process, whereas the reverse process converting a vapor into liquid is called your condensation process. For the condensation to takes place, the vapor should come in contact with a solid surface whose temperature is less than the temperature of saturation for this vapor or the liquid. Next we will go for Newton's law of cooling, which will tell you as calculating total heat transfer by means of convection. Let us say we consider there is a solid surface and adjacent to the solid surface there is a fluid, and the temperature inside the solid surface is varying, let us say with space x. So, on the surface if you measure, you will have some particular temperature, let we denote as T subscript s, that is temperature on the surface. Then temperature of the ambient fluid we denote as T infinity, which we consider to be some constant value, and here suppose we assume that the temperature of the solid surface which is exposed to the fluid is higher temperature compared to the ambient fluid, that is T s is greater than T infinity. So, in that case there will be heat transfer by convection from this solid surface to the ambient fluid. So, this heat transfer by convection from this hot solid surface to this cold ambient fluid. So, we will represent it as Q convection. This is directly proportional to the surface area which are in direct contact with the ambient fluid. Then this convective transfer is also directly proportional to the difference in temperature between the hot solid surface and the cold ambient fluid. That means, mathematically you can write down Q convection is directly proportional to A into T s minus T infinity, how unit will be in watt, or you can write down Q convection will be equals to H into A into T s minus T infinity. Here this small h, that is your constant of proportionality known as the convective heat transfer coefficient. And if you take the surface area A to the right hand side, so you will get Q convection by A, that is convective heat transfer per unit surface area of the solid to the ambient fluid, that we represented as Q double prime convection, that will be equal to H into T s minus T infinity. And from this expression where this flux will be unit will be watt per meter square, you can keep this H on one side, take everything to the other side. So, you will obtain an expression for this heat transfer coefficient H, that will be equals to convective heat flux divided by difference in the temperature between the hot surface and the cold ambient fluid, that is Q convection flux divided by T s minus T infinity, that is your convective transfer coefficient, for which the unit is watt per meter square Kelvin. And regarding the direction of heat flow, so here it will be normal to the solid fluid interface, and here in this case it will be away from the surface, because here we consider that T s is greater than T infinity. So, heat will flow from the solid phase to the ambient fluid, that way direction will be away from the solid surface and normal to the surface. So, here we can indicate this to be the direction in the present situation. Let us say we consider another configuration where the left face of this solid surface is exposed to the ambient fluid. So, the scenario is shown here, this is the solid and this is the fluid, and here we consider that the surface is at higher temperature than the ambient fluid, then in that case the direction will be changed, it will go towards the other side, that is it will go towards the fluid here as shown here. That means, when the solid surface is at higher temperature, the flux direction will be away from the surface towards the fluid. If we consider another situation where we consider that the ambient fluid temperature is higher than the solid surface temperature, then in that case there will be transfer of heat by convection from the fluid to the solid surface, and from the surface it will heat will penetrate into the solid by means of conduction. So, inside the solid there will be conduction, and here on the surface there will be convection. So, in this case the direction of heat flow will be from the fluid towards the surface, because the fluid is at higher temperature compared to the solid. Similarly, if you change the orientation as shown here, in this case again considering that the direction will be from the fluid toward the surface, see in this case the arrow will be towards the right hand side, where in this situation the arrow will be towards the left hand side. And this heat transfer coefficient H, it basically depends on the surface heat flux Q double prime and the difference in the ambient and the surface temperature, that is T s minus T infinity. So, this we obtained from this expression, H depends on Q double prime and H depends on this delta T. So, this we get from this mathematical expression, but in reality the convective heat transfer coefficient H, it will depend on the condition of the flow in the boundary layer, that is whether flow is moving or not and other types of fluid, everything will decide the value of H here. So, you will see H basically depends on the flow condition near the boundary, whether the flow is laminar or turbulent. When it is a turbulent flow, there will be convective heat transfer coefficient will be higher compared to the laminar flow. So, in such case the heat transfer by means of convection will be more in case of turbulent flow compared to the laminar flow. This is because there will be continuous mixing of the fluid in case of a turbulent flow, whereas in a laminar flow the fluid do not mix with each other. Then this H will also depend on the surface geometry and the total surface area and the thermophysical property of the fluid. So, all these 4 together will decide the value of heat transfer coefficient H for a particular engineering problem. So, the typical convective heat transfer coefficient values here I have listed for a few things. For example, if we consider free convection, in that case for gases the value of convective heat transfer coefficient H will lie in the range of 2 to 25 watt per meter square Kelvin, whereas instead of a gas for a liquid, for the same free convection the heat transfer coefficient increases by around 2 to 40 times from around in the range of 52,000 watt per meter square Kelvin. For forced convection for gases, the convective heat transfer coefficient will be lie in the range of 25 to 250, and for liquid it will increase to the range of 100 to 20,000. In case of a forced convection, the heat transfer coefficient increases many times compared to the free convection, and because of this the total heat convective heat transfer in case of a forced convection will be very higher compared to heat transfer by means of free convection. Then when you consider convection with phase change like the boiling and the condensation process, again there will be a increase in the value of this convective heat transfer coefficient H, which lies in the range of 2500 to 100,000 watt per meter square Kelvin. So, that means if you go for a phase change process, then you will be able to make more amount of heat transfer by means of convection. It is to note that this convection heat transfer is a separate mode of heat transfer from the conduction, where conduction takes place in solids as well as in fluids near the boundaries, whereas convection takes place purely in the fluids only which are in contact with the solid surface. We will be frequently using this convective heat transfer while solving problems on heat conduction as part of the boundary condition, that is condition on the boundary. So, while solving problems on conduction, since we have to deal with heat transfer as a part of the boundary condition, in such problems we will assume that the heat transfer coefficient H is known to us, and we will go for solving the problem on heat conduction, where we will try to find out temperature distribution inside the solid and find out heat transfer in between the solid from one point to another point or one zone to another zone. So, with this we will conclude the lecture for today, then we will carry forward in the next class from this point onwards. Thank you.